Continuing with our concepts of Lagrange's equations in our review of mechanics, we're going to do a very simple example just to show how Lagrange's equations work with generalized coordinates using what is called the Atwood's machine. The Atwood's machine is basically a very simple device that has two masses that are connected by a massless cord that does not stretch, that goes over a pulley. That cord has a length L, and therefore we can think from this pivotal point right here that the distance down to mass m1, which hangs on one side of the cord, is a distance x. The distance then, since the cord has a length L, down to the other mass is a length L minus x. We therefore form the Lagrangian by first forming both the kinetic and the potential energy. The kinetic energy is, of course, the sum of the two kinetic energies, which is 1/2 m1 x dot squared plus 1/2 m2 x dot squared. The reason is in the derivative of this one, we get the time derivative of x squared, and the time derivative over here, of course, eliminates L, and it takes the negative sign, and since the term is squared, this negative sign disappears. Therefore, the sum of these two kinetic energies is given by T in this expression here. For the potential energy, we have both negative terms relative to a height right here where the pulley is, minus m1 times g times the height, which here it would be the depth below that point, minus m2g times L minus x, which is the distance down here. That gives us the total potential energy V using the equation mgh for mass times gravity times the height in a gravitational field that we learned as a freshman. Therefore, our Lagrangian is formed as T minus V, which is going to be 1/2 m1 plus m2 x dot squared plus, because of the minus signs cancel here, m1 gx plus m2g L minus x. Now, recalling Lagrange's equations given by this expression here, we must first find the partial of L with respect to x, and when we do that, remember that x and x dot are treated as independent variables. So we get two terms. The partial of L with respect to x gives us an m1g, and over here it gives us a minus m2g because of this minus sign here. The constant term, of course, the partial derivative of that with respect to x vanishes. Then we have to find this other term, the partial of L with respect to x dot. That gives us a factor of 2, which cancels the 1/2, m1 plus m2 times x dot. And that's exactly what we have here. So it is the time derivative of this term here minus this term here must be 0. And that becomes the time derivative of this term here becomes m1 plus m2 x double dot minus the partial of L with respect to x, m1 minus m2, g is equal to 0. Consequently, we can bring this term to the right side of the equation and divide by m1 plus m2 to get x double dot, the acceleration of the system, is m1 minus m2 divided by m1 plus m2 times the acceleration g. The quick way to check this to make sure that you got the signs right is to do the following. As you know, if m1 and m2 are exactly the same mass, then of course the system will be balanced and there'll be no acceleration at all, just a constant velocity or no motion at all. If m1 minus m2, if m1 is equal to m2, then of course this acceleration vanishes, which is exactly what we would anticipate. Likewise, you can also check the equation by saying, what if m2 were not here? And you just have a mass m1, and then of course the mass m1 could go into total free fall. Then if m2 is equal to 0, these two terms vanish. m1 over m1 is 1, and the acceleration of the system is equal to g, which is exactly what we would expect from m1. Lagrange's equations allow a formulation of the dynamics in terms of generalized coordinates, velocity, momenta, and forces. These concepts, in turn, help specify and solve problems involving constraints, and that's the primary use of Lagrange's equations. But more important here underlies their formal value in providing a deeper view into the laws of nature, along with a different form of mathematics. The Lagrangian, as we'll see later, is very important in alternative forms of mathematics, as well as systems that have conservative forces, generalized coordinates, and constraints. Again, continuing our discussion and review of classical mechanics, the next formulation of classical mechanics is done in terms of Hamilton's equations of motion. We can consider here a Lagrangian, L, which is, of course, as we have been using, defined as a function of the generalized coordinates, the generalized velocities, qi dot, and the time t. And it is dependent upon n different variables, the qi's, which are all independent, and n other variables, qi dot, which are independent of each other as well as the q's. We define the generalized momenta, as we did when we worked with the Lagrangian, as pi, which is the partial of the Lagrangian with respect to qi dot. Then we define the Hamiltonian as a function of p, q, and t. And notice that we have changed variables here. So we're no longer using the q dots as independent variables, but rather a set of p's that are now considered to be independent, defined by this set of equations here. The Hamiltonian is defined as the sum over I of qi dot p I summed over all I minus the Lagrangian itself, where in that function we have removed all dependence upon the qi dots by inverse solution of these equations here. It can then be shown that Lagrange's equations, and therefore Newton's equations, are totally equivalent to the following set of equations. Qi dots, in other words, the derivative of the generalized positions, are the partial of the Hamiltonian with respect to the pi's. And the pi dots are the derivatives with a negative sign of the partial of h with respect to qi. We then finally find that the negative of the derivative of the Lagrangian, the partial of the Lagrangian with respect to time, is the positive partial of the Hamiltonian with respect to time. This set of equations are called Hamilton's equations. In a certain sense, we need to realize that what we have done is we have gone from n different equations involving the q's and the q dots as independent variables to a set of 2n equations for the q's and for the p's, and this gives their time derivatives. And these equations are, of course, all coupled. So we have n equations of this form and n more equations of this form for the time derivatives of the generalized momenta. Down underneath, we can kind of guess what these equations mean. These equations here say that the velocities are the time derivatives of the Hamiltonian with respect to the momenta. These equations here said the momenta, time rate of change, is going to be the partial of h with respect to q's. So this equation here are going to give the forces. This equation over here is going to give the velocities in terms of the Hamiltonian. If the equations of transformation, r is equal to r of q and t, A, do not depend explicitly on the time. In other words, there's no explicit dependence, only implicit dependence upon the time through the q's. And B, if the potential is velocity independent, then, and only then, does it follow that h is equal to t plus v and is the total energy. It is important to note here that the Hamiltonian can be a constant of the motion and still not be the total energy. In most of our systems that we think of, the Hamiltonian is the total energy of the system, and it is also a conserved quantity. When we get to the discussion of Lie groups and Lie algebras, and especially in quantum theory, the Hamiltonian is central there in helping us understand the time evolution of the system. The Hamiltonian, in fact, will be the generator of time translations of the system, and therefore play a very crucial role in generating a set of motions that's very similar to the type of motions that we have in an n-dimensional space for our Lie group as dependent upon a Lie algebra. In order to get a better feeling of Hamilton's equations, we're going to solve a very simple problem with Hamilton's equations. Let's consider a mass that's moving in 2 dimensions with a central force that's defined by a potential that is dependent upon only upon the radius and not upon the angle. So we have a central force defined by V of r. Well, obviously the position can be written in terms of these coordinates as r times cosine of theta, where y is equal to r times sine of theta. It follows then that the time derivative of x dot, is equal to the derivative of both of these terms. First, the r dot times cosine of theta, and then the derivative with respect to theta. And here we take the derivative of cosine, giving us a negative sign, and then the negative of the sine has a term that comes out, which is r dot. Likewise here, for the time derivative of y, we end up with y dot is equal to r dot sine theta plus r, because we're taking here the derivative of the sine, which does not give us a sine inversion, times the cosine times theta dot. Then we can write the total kinetic energy as 1/2 m x dot squared plus y dot squared. Well, we have to here put in x dot and y dot in terms of the new polar coordinates r and theta. When we do that, we get 4 terms. 1/2 the mass times the squares of all of these terms. That will give us, in particular, r dot squared, cosine squared. Now here I've just left out the theta so that it doesn't look quite as confusing. Cosine squared, r squared here, theta dot squared, sine squared. And then we have plus 2 times the cross product of these 2 terms. So that's 2 times, with a minus sign, r dot, r, theta dot, cosine theta, and sine theta. Plus, likewise, the cross terms here, and the individual squares, r dot squared, sine squared, plus r squared, theta dot squared, cosine squared. We notice here that these 2 cross terms both cancel, one being of a positive sign, one with a negative sign. And here we have a sine squared plus a cosine squared, both multiplied by r dot squared here. And over here, a sine squared plus a cosine squared, with the term r squared theta dot squared multiplying each one. As sine squared plus cosine squared is equal to 1, it follows that we get the kinetic energy as 1/2 m r dot squared plus r theta dot quantity squared. And that becomes our kinetic energy in polar coordinates. We now have to express h in terms of the momenta. We can do that by writing the momenta, writing the Lagrangian, is t minus v. And of course, v is going to be v of r, and that's all we know about it. It's a central potential. And so when we find the generalized momenta r, it's going to be the partial of r with respect to r dot. Therefore, by taking the derivative of this, since there is no r dot in this part of the Lagrangian, the partial of L with respect to r dot is the partial of this term with respect to r dot, which is going to bring down a factor of 2, which cancels the 1/2. It's going to be m r dot. Likewise, to take the partial of L with respect to theta dot, we get this term right here, 1/2 m times 2, which kills the 1/2, theta dot times r squared, because there's an r squared term here. This gives us our radial momenta as m times r dot, and our angular momenta, m r squared theta dot. Consequently, doing the inverse solution, we can see from this equation that r dot is the radial momenta divided by m. And theta dot from this equation is equal to p theta divided by mr squared. We now have to put those into the Hamiltonian, which is t plus v. Now t plus v, if we plug those in, we get 1/2 m momentum in the radial direction squared over m squared plus 1/2 m r squared times the theta dot squared. Now here we're going back to this term right here and putting the theta dot in, plus v, which is the potential. One of the m's cancels here, and we get pr squared over 2m, plus, simplifying the second term, we get a cancellation of one factor of m, so we got a 2m. R squared cancels two of the factors of r in the denominator. We get p theta squared, the momenta in the theta direction, divided by 2mr squared, plus the potential. The Hamilton's equations are then as follows. R dot is partial of h with respect to PR. Well, we can take that very quickly by taking the derivative of this Hamiltonian, which is right over here, and we take the derivative with respect to PR. There's no PR here, no PR here, so we get 2PR over 2m, which gives us PR over m, and that gives us R dot. We can find theta dot as partial of h with respect to the momentum in the theta direction. That term only occurs here. Taking that derivative, we get 2, which cancels the 2 in the denominator, p theta over mr squared, and that gives us theta dot. We have two more Hamilton's equations. PR dot, the momenta in the radial direction, is going to be the negative of the partial of h with respect to r. Now, when we look at that, r occurs in two places. R occurs here, and r occurs here. R occurs here to the factor minus 2. So when we take the derivative with respect to r with a negative sign, we'll get this minus sign will kill the minus sign that comes from the r to the minus 2. We'll get an r to the minus 3. And also, from this term here, the partial with respect to r will give us a minus partial v with respect to r. Finally, the momenta in the theta direction, dot, is going to be the partial of h with respect to theta, and no theta appears. Therefore, the momenta in the theta direction is unchanged in time. We can look at this, now collecting these four equations together, in the following way. The momenta in the r direction is mr dot, exactly what we would expect from this equation right here. We've simply taken the mass, multiplied it over here, and that kind of justifies what we would think intuitively. It says that the radial momenta is the mass times the radial velocity. Not necessarily something that would be correct, but something that our intuition would say is correct. The momenta in the theta direction is mr squared times theta dot. This is the angular momentum. We see the corresponding equation for the derivative of that says that the radial momenta has a time derivative which is 0, which means that it is unchanged. Consequently, angular momentum is conserved. The radial momenta, on the other hand, changes in time according to two factors. One, which is the force radially, that comes from the negative of the derivative of v with respect to r, so we have defined that as the radial force, and another term here, which is basically comes from a centripetal type of force, p theta over mr cubed. The Hamiltonian formulation is very important in quantum theory, and the momenta in general are much more important than the velocities are in physics. So it's very important that we have a feeling not only for the Lagrangian, but also for the Hamiltonian equations of motion. Here they are given in a simple example. Continuing now with our review of classical mechanics, we want to discuss the variational principles that can be used to define motion. There's a principle called Hamilton's principle that states that any variation in the integral of the Lagrangian between one time and another time must be zero for the actual motion that takes place physically. This principle can be shown to be a necessary and sufficient condition for Lagrange's equations, and therefore for Newton's equations, and also for Hamilton's equations. It's written in this form right here, that the variation in the integral from time t1 to a time t2 of the Lagrangian with respect to time must be zero. Now if we envision that as a path that goes from one place to another, then that path, any variation in that path will give us zero. That is the extrema of the motion that actually takes place. The delta symbol refers to a variation in the path that leaves the endpoints fixed. The principle states that the actual motion of the system is an extrema, that is a maxima or a minima of that particular motion. Since we know the relationship between the Lagrangian and the Hamiltonian, we can convert that integral to another form, which is in this form right here. So it's a variation of the integral from time t1 to t2 of the sum of all the pi qi dots minus the Hamiltonian. And if we take that entire term, the variation of it is equal to zero. The principle of least action states that in a system for which h is conserved, and we use a delta variation as opposed to the written a different way as opposed to this delta variation, which requires that the h be conserved along all the varied paths, we get a principle of least action that looks like the following. Any change, and that's the variation that requires that h be conserved along the paths, therefore this term will vanish. Integrate the integral between t1 and t2 of the sum of pi qi dot summed over all I, integrated over all time between t1 and t2 is equal to zero. The variational principles have a philosophical simplicity and a formal power and beauty. It tells us really that as we look at the actual motion that takes place, something is an extrema. It's either a minima or a maxima. And psychologically, that's very satisfying. In quantum theory, this can be related back to what is called a Feynman path integral formulation. And in that Feynman path integral formulation, we find that the particle in quantum theory actually goes from one position to another along some path, along all possible paths, but the longer the path, the more the phase changes. So a slight variation in a real long path results in a big change in the phase, which will cause interference. Therefore, it follows that paths that are very distant from the minimal path interfere very easily with themselves and therefore are very unlikely. This was an incredibly beautiful formulation of quantum theory due to Feynman, and can be shown to be exactly equivalent to the regular Heisenberg or Schrödinger equations or Dirac equations of motion for quantum theory.